In this video, I'm going to go through a number of conceptual questions. These conceptual questions are all going to relate in some way to resistors. Resistors in series and parallel, current flowing through them, power. So all these different concepts we've talked about in relation to resistors. And as usual, pause the video and answer it yourself before watching the solution. So here is our first question. The correct answer here is C. Now, an ideal wire, we're assuming connecting wires have zero resistance. Now, whether or not that is a good assumption depends upon how much resistance that light bulb has. Connecting wires, as long as they're not really long, typically don't have much resistance. And so it's not necessarily a bad assumption. As we think about this current that is flowing, we now have a junction right here, meaning current could go through the light bulb or through the wire, or both. There could be some of both. That makes this wire now in parallel with the light bulb. If you think about what two resistors, if they were both resistors, needed to have in common, in parallel, they must have the same delta V, same potential difference. For the light bulb, that delta V would be however much current is flowing through it times its resistance. For the wire, we would also use I times R. But R is 0. If R is 0, then it doesn't matter how much current would flow through it. But if R is 0 up here, it needs to be 0 for the light bulb as well, which means I must be 0 for the light bulb, because the light bulb has a resistance value. R is not 0. So to get a delta V that is the same, both being 0, the current through this light bulb would be 0 if that wire was ideal. All the current would go through the wire. This would be we would short circuit the light bulb, not have any current flowing through it. You may have heard that current takes the path of least resistance. That's where this comes from. Here, the least resistance is the wire, so all the current goes that way. Now, if we had in parallel the light bulb with something that had resistance, some current would go through both. They would not have the same amount of current unless they had the same resistance as well. Whichever resistor was bigger would have the least current. Okay, we have another question here. What do you think about this one? The correct answer on this one is D. To find the value of current, we know both of these resistors are going to have that battery current flowing through them. There's no other path for those charges to take. So we can look at this as an equivalent resistance. These guys being in series, we simply add their resistor values together. So we get 18 ohms. Well, the current that flows is going to equal the potential difference divided by the resistor. When we have a loop with only one resistor, this resistor will have the entire battery voltage across it. So 12 volts over 18 ohms. Let's see, 6 goes into there. So 2/3 of an amp would be flowing out of the battery through both resistors and back into the battery. So the current depends upon the battery voltage and the equivalent resistance. Even though this question isn't asked, let me ask it. Would these resistors dissipate the same power? So if they were light bulbs, for example, would they be equally bright? And the answer is no. And that's because they do have the same current flowing through them, but they have different resistor values. Now, one way we can write power is I squared R. I know they have to have this 2/3 of an amp flowing through, but because they have different resistors, or resistances, I should say, they will have different power. So this would be 5.3 watts. This one would be 2.7 watts. The larger resistor in this case would have more power because they have the same current in series. All right, so we get 2/3 of an amp here. Let's look at this next question. The correct answer here is A. That's a lot more current than the previous example. We have the same battery voltage. We still have a 12 ohm and a 6 ohm resistor, but they're connected in parallel, where they have to have the same potential difference. This battery current that's labeled is both coming out of the battery and coming back in. But as it continues and reaches this junction, it's going to split. Some of the current will come through the 12 ohm resistor, and some of the current will come down through this 6 ohm resistor. This is a conservation of charge rule, and technically flowing charge. Whatever charges are moving must continue moving. We can say that the battery current flowing towards that junction gets split up into I1 and I2. But I1 and I2 have to add up to be that battery voltage. Now notice down here, I1 and I2 come back to a junction. Here they are both coming towards the junction, and they combine back together to become I, the battery current. This is a junction rule, is what we call it. It has to do with the conservation of charge. Whatever charge is moving must continue moving. Now, in terms of how much current flows, there's two ways to go about this. We can totally find an equivalent resistance, and that will be the battery voltage. Well, sorry. Let me explain that better. We can find an equivalent resistance. These two are connected in parallel. To find equivalent resistance, we have that inverse relationship. So we would have 1 over R equivalent is 1 over 12 plus 1 over 6. If I get a common denominator, 3 over 12 or 1 over 4, then I have to flip it. This is 4 ohms. Those two resistors, the 12 ohm and 6 ohm in parallel, are equivalent to having a resistor of 4 ohms attached to our battery. The current then that comes out of the battery, goes around and comes back in, this battery current will be the potential difference of the across the resistor, which is the battery's voltage, over the resistance. So 12 volts over 4 ohms is 3 amps. The other way to think through this, which is just as good essentially, we know that these two resistors, the 12 ohm and the 6 ohm, are in parallel with each other. If we follow a path around the circuit, I know whatever the battery puts in has to come out or be a drop across the elements in the circuit. If I take this left-hand loop, the only element I pass is the 12 ohm resistor. So that 12 ohm resistor must have 12 volts across it. Well, using I is delta V over R, we find that this I is 1 amp. 1 amp of current needs to flow through that resistor in order for it to have a voltage of 12 volts. The other path I can take is over through this 6 ohm resistor, and that will take me back to the battery. That means this 6 ohm resistor also has a potential difference of 12 volts, because that was the only element I passed by other than the battery. So the 12 volts is put in by the battery, the 12 volts has to be then across this one resistor. Well, current is V over R. This would be 2 amps. And we know the battery current has to equal the I1 plus the I2, which is 3 amps. So following the path around the circuit is a loop rule. We'll talk about these rules more in the next video. The current splitting up at a junction or coming back together at the bottom junction is called a junction rule. And these rules must be satisfied in our circuits. Anyway, battery current, 3 amps. Next question. Correct answer here is C. If they're identical light bulbs, that means they would have the same resistance value. They're connected in series. I can see that I'm going from the positive end to this light bulb, from this light bulb to the next, from this light bulb back to the battery. That means they are in series with each other, so they have to have the same current. Same current, same resistance, they're going to have the same power. All right, we have another question here. What do you think about this one? The correct answer is A. The current changes because the equivalent resistance of the circuit changes. Before the switch is closed, we may as well not even have R2 drawn. Our circuit is the battery and resistor 1. Having the switch open up here makes it so there is not a complete path for charges to take. And so no charges will come this way. So no current will flow to R2 when the switch is open. Okay, when we close the switch, we now have our battery, we have a resistor 1 and a resistor 2 in parallel. There is a complete path for charges to flow through. R1 and R2 are in parallel. The equation to find an equivalent resistance is this inverse relationship. That means R equivalent is smaller than R1 and R2. If the equivalent resistance goes down, the battery current, the current flowing out or into the battery is equal to the battery voltage over the equivalent resistance. So the equivalent resistance is now smaller, which makes the current flowing from the battery bigger. Okay, next question. The correct answer here is E. Again, it has to do with the change in overall resistance, equivalent resistance in the circuit. Now here, since we're talking about brightness of the light bulbs, we're thinking power. Before that switch is closed, we essentially have these two light bulbs in series. So the current that is flowing, this current, depends upon the equivalent resistance of the circuit. It depends upon both light bulbs. Once we close the switch, we're assuming ideal wires. If the switch is closed, then all of the current is just going to go down through that middle wire. No current through B. And that's because the path here now that had the switch in it has no resistance. So its delta V would be 0. The delta V for light bulb B has to be 0 as well, because this wire is in parallel with light bulb B. Therefore, they must have the same delta V. The only way for light bulb B to have a delta V of 0 is to have no current. So B goes out. Now, why does A get brighter? A gets brighter because we essentially just have A connected to a battery. So the current that flows supplies light bulb A with the entire battery voltage. Or we can think of that as the battery voltage is spread amongst a smaller equivalent resistance. We've gone from having 2R equivalent to an R equivalent of simply R. So if R equivalent gets smaller, the current gets bigger. And thus, brighter. The bulb will be brighter. Here is another question. B is the correct answer. Now power, one way to write that for a resistor is delta V squared over R. The reason I want to choose this version is I already know their R values, their resistance values, and I know both of these have a delta V of 9 volts. I can see that both because they're in parallel, but also if I followed a path from one end of the battery around, I would pass through either the 9 ohm resistor or the 1 ohm resistor. So they have to have the 9 volts. So they have the same voltage, but different resistor values. So now by looking at the power in terms of just one thing in the equation that's different, I can compare them. So larger power is going to be for the 1 ohm resistor because R is in the denominator of this equation. Smaller R means a larger power. So I always write the power in terms of whichever variables I know one is constant and one is changing or different, so that I don't have to account for two things changing. So for example, those two resistors will have different amounts of current. So I wouldn't want to look at I squared R because they have different current and different resistors, unless I, of course, actually solve the problem and calculate the numerical value, which I don't need to do. All right, one last concept question. Okay, the correct answer here is A, which is confusing at first. When we have a 60-watt light bulb and a 100-watt light bulb, that is based off of assuming they are going to be connected individually to a power source. So the power rating is based off of, let me write that again. Power rating is based off of assuming they're going to be attached individually to the same power source. Meaning we assume that they're going to have the same delta V. If that were the case, meaning I attached just the 60-watt light bulb, or I attached just the 100-watt light bulb, is what this is based off of. If that were the case, they would have the same delta V. So when we think of the smaller power comes because of a larger resistor. The 60-watt light bulb has a larger resistance compared to the 100-watt light bulb. When we connect them in series, they're not necessarily going to be 60 watts and 100 watts because they're not connected to the same, they will not have the same delta V across them. What they do have in common is the current that will flow through them. If they have the same current but different resistors, now the actual power we would look at as I squared R. Actual power. Same current but larger resistor means a brighter bulb. Okay, a little confusing, I know. 60 watts and 100 watts are essentially ratings of these bulbs. Ratings probably not the right word, but that's the word coming to me at the moment. In order to say I have a 60-watt light bulb, that has to be based off of some assumptions. And again, the assumption is I'm going to attach that, say, to the wall outlet, for example. And so if I attach a 60-watt light bulb, I put it in a lamp, I attach it to the wall outlet, this 60-watt light bulb would be different than having my 100-watt light bulb in its own lamp that I put on my end table or I put on my nightstand near my bed. So these 60 watts and 100 watts, they're labeled that based off of assuming they're going to be the only light bulb in the lamp. So when they label the 60 and 100 in the circuit, they're essentially giving us two specific resistor values of sorts. So we had to reason out which one had the larger resistance and smaller resistance based off of the assumption that they were alone connected to a power source. So a less bright light bulb connected to the same power source would have to have a larger resistance. And now coming back to this circuit, a big resistor versus a smaller resistor, but they have to have the same current, they're going to have different power. So they're not going to be glowing at 60 watts and 100 watts per se. How they end up glowing depends upon how they are connected together to the circuit. So conceptually is really remembering these rules, conservation rules like the junction rule and the loop rule. The concepts behind this tend to be trickier than the equations themselves. So make sure you're practicing the concepts as you're working through the homework, and please reach out if you have questions. I'm happy to answer them.